Okay, welcome back everyone to week 4, I think we are now. So this will be the third week of this bit, and just a bit of a recap to start us off of where we got to last week when we were looking at different types of decision roles. So previously we got to the point where we wanted to look at classification. So last week we covered the idea of classification, particularly the idea of the Bayes decision rule, where we want to try and find the classification that maximizes the a posteriori probability, so the probability of the class given the observation. So the prior probability is the probability of the class without making the observation. The posterior probability is the probability of the class after we've made the observation. So that's this prior and posterior idea. We talked a little bit about errors, but then we introduced the idea that we're going to build a parametric model of the class. And in particular, we want this idea of the class probability, which is, in order to calculate our P of, let's go back to our Bayes rule again, where we have I've got a Bayes rule back on a previous slide, I think, but Bayes rule back here. In order to do the probability of the class given the observation, then we need the probability of the observation x given the class omega times the probability of class omega divided by the probability of the observation. So this is our prior. This is then the class conditional probability, and then this is the posterior probability. So if we want to find the maximum of this over different omegas, the x is all the same, so we just need to find the maximum over this term here. So this means that we need to make some assumptions about what the prior probabilities are. In some cases, if we don't know anything else, we'll just assume that they're the same. But in some other cases, we'll make assumptions about different prior probabilities. Perhaps if, well, I suppose if there's something topical, you could talk about probabilities of a particular disease being around, then, what's the likelihood of that, and therefore what's the likelihood that a particular test for that disease will pick it up. So we can look at the probabilities of, given an observation, that we would have that. But if we make those prior assumptions that we're going to measure from what likelihood the classes are going to be around, we also need to have this class conditional distribution. What's the distribution of x given our class omega? And that's the thing that we're going to need a model for. So that's where we then started on forward, the type of parametric decision rule. So parametric means defined by parameters, and the particular type of parametric decision rule that we're going to use is the normal or Gaussian distribution. So this is the type of distribution that we've got. We've got some mean mu, and for a particular class it's the mean mu I, and then we've got a standard deviation sigma, or sigma squared we usually will work on in the one-dimensional case. So this is the thing that we'll be familiar with, but we're actually going to use the multi-dimensional version of that. So the mean and the variance, or in this case the mean and the covariance matrix, these are the parameters that define our model. This is why it's a parametric model. So in this case, our probability here is going to come out from knowing these parameters and being defined by x. So what we're going to do in the next part of this lecture, once we've actually explored a bit about what shape of boundaries this makes, we're then going to look at how do we estimate these parameters. Somebody could tell us, it might be that you might know the probabilities of this because you've designed your class to have a certain mean and a certain variance. But in reality, we're estimating the parameters of those, and we have to estimate them from data. And this is where the idea of supervised learning comes in, that we make those estimates based on the assumptions that we have a particular model, and then we want to learn those parameters. So this is the generalization of the one-dimensional Gaussian. We gave some examples that we looked at last time in terms of different means and covariance matrices. And then we looked at the types of decision rules that we could get. Now, I did this on paper, but this is the summary on the slides for that as well, that if we want this decision rule, that the probability of omega I, which is the class that we're going to choose, we want to assign a particular variable to a class dependent on the one that maximizes the probability of that class given x over all of the possible classes. So this is the maximum a posteriori rule that we introduced last time. It says, look at all the classes, what's the probability of each class given that observation, and then assign it to the class that has the maximum value. And that is the one that's going to, in one sense, it seems the obvious thing to do in that you're choosing the most probable class. But in terms of the error measure that we introduced last time, it also minimizes the probability of error. So you can think of it two ways. You can either say, we're going to choose the most probable class, or we're going to choose the class that reduces the error as much as possible. And if our error measure is something slightly different, so if some errors are more costly than others, we may end up with a slightly different rule to that. One of the next tutorial questions for tutorial 3 will look at that to see happen if you have a different error rule. So then we looked at substituting in this parametric model. So we've got now our multivariate Gaussian model. That's going to be the thing that we use for P of x given omega in our, this is our class conditional probability density. That's the thing that we use here with a sigma and a mu for each of our classes. And then we say, right, what does that turn out to give us for our decision rule? And this is what we looked at right at the end of the lecture, but I want to just go through that again, just to sort of recap where we go. So the key things that we can spot in here is that there is a dependence on x just inside the exponential here. So there is a dependent on the class through this determinant of this covariance matrix and through this mean. But the determinant of the covariance matrix is fixed for a particular class. Once you've chosen the class and you know the covariance matrix of it, that's a number. So all of this thing here is a number. Inside this exponential is the thing that's dependent on x. And if we want to see a better idea of where the boundary is, if we take the logs of both sides, then it gets rid of this exponential here, and so this gives us this term. So things like this term here, which if I write it out on the board in another way, this is our P of, in this case, P of x given omega is 1 over 2 pi to the n sigma I determinant square root of all that times the e to the minus a half x minus mu transpose sigma to the minus 1 x minus mu. So we've got these two terms. If we take the log of this, then this comes out as a squared a quadratic term, and this comes out as a sort of constant value for that particular class. We ended up with this rather awkward term, but but we can simplify this by pulling out a constant here, which gives us this new rule now. So this is the rule that we ended up with at the end of last lecture, that we assign x to omega I if this measure is the smallest of this measure here. And this is quadratic in x. We can see it's got an x minus mu transpose sigma times 1 x minus mu, weighted by a sort of constant. So what I want to just do now to take on to the next stage of this is see what types of rules do we end up with if we make certain assumptions about how these things are related. So what if the class prior probabilities are the same? What happens if the covariance matrices for all the classes are the same? And we can find we get some simplifications that happen in that case. So in fact, to do that, I'm going to go back over to the visualizer slides over here and just recap back to, this is where we got to on the visualizer from last time. So we had this term here where we've really written out what was on the slides in there. I'll zoom in so that we can see that a little bit more clearly. So we've got here that this value, which has got a sort of negative on this time, is the maximum of this with a negative here plus this Cj and Ci's. So we can sort of see already that if the Ci and the Cj's are all the same, then it's only going to be dependent on this sort of quadratic measure here. Also, if this covariance matrix is an identity, what's x minus mu I transpose x minus mu I? What is that in terms of some sort of measure of how x is different to mu I? It's a dot product, yeah. So if we look at the dot product from there, it's a dot product of the difference between x and mu I, which is actually just the distance. It's the squared distance between the two. So actually what we'll see as we work this through is that in certain simple cases, like identity covariance matrix and equal prior probabilities, this rule will turn into find the nearest mean. So although we started from something that looked really complicated, actually in some cases this will turn into something really much simpler that corresponds to something that we might think of. We've got two models, a mean over here and a mean over here. Here's a new point, find the nearest mean, assign it to that. And that's a really easy rule that we can apply. So let's just work through those and see how this comes out so that we can actually see this working. So we've got, let's start on the next slide for this one. I'll just rewrite this term out. Have we got that at the top? Oh, I'll need to turn off the autofocus so it doesn't try and focus on my fingers instead of. Okay. So let's just write out this term minus x minus mu I transpose sigma I to the minus 1 x minus mu I plus Ci is equal to the maximum from j equals 1 to n of minus x minus mu I transpose sigma j to the minus 1 x minus mu I plus constant term Cj. So let's try a couple of things to see what we might get. So from that rule, so this is 20, 19, 20. So let's try equal covariance. So let's suppose that sigma I is equal to sigma j, and we'll just call that sigma. So let's see what happens when we substitute into here. So we get minus x minus mu I transpose sigma to the minus 1, x minus mu I, plus ci is equal to maximum from j equals 1 to m of minus x minus mu j. These should be j's up here, by the way, sorry. X minus mu j transpose sigma to the minus 1, x minus mu j, plus cj on that side. So let's try expanding out this to see what we get in terms of a sort of rule for this expansion. So let's expand out this time. So x minus mu I transpose sigma to the minus 1, x minus mu I. Let's have a look at what that turns into in terms of expanding these different terms. So we've got x sigma to the minus 1, or x transpose sigma to the minus 1, x. So that's choosing the first two terms of this, plus minus mu I transpose sigma to the minus 1, x. We've got an x here with a minus mu I on that side, so a minus x transpose sigma to the minus 1 mu I there. And then we've got a minus mu I transpose times minus mu I on the other side of the sigma to the minus 1. So then we've got a plus mu I transpose sigma to the minus 1 mu I. So this is a squared term here, but this one, mu I transpose sigma to the minus 1x, is a scalar value. This is just a scalar value, and actually that is equal to its transpose here. This is also a scalar value. So this is equal to minus 2 mu I transpose sigma to the minus 1x. So it's a scalar value because this is, if we think of let's take an aside here. So if we have A transpose B, that's a scalar, and A transpose B is equal to B transpose A. There's a similar thing. No, it's an important point though. I think it's useful if we have C transpose M D, then C transpose M. Let's suppose that C transpose M is equal to some matrix, some vector E transpose, then C transpose M D is equal to E transpose D, which is equal to D E transpose, which is equal to D M transpose C. So this is the sort of thing that is useful to remind yourself of matrices and vectors, how these multiplications work. So this bit tells us, for example, this x sigma to the minus 1x is a squared term, but there's a vector here, mu I transpose sigma to the minus 1, that's dot producted with x. And so this is going to be a useful thing that will come out later. And this is not dependent on x at all. So given a particular class, this is going to be a constant. So let's try this and see see what happens on the next line. So we've got equal covariance here. Yes, question. So, yes, you're quite right, of course. D transpose E, the transpose is just in the wrong place, yes. So let's now see what happens to this rule at the top if we substitute these in. So we now, instead of this term up here, when we want to substitute all of these in, minus x minus mu I transpose sigma I to the minus 1 x minus mu I plus ci, that will become x transpose sigma to the minus 1 x transpose we've got a minus sign in the front of that one, plus 2 mu I transpose sigma to the minus 1 x. Sorry, that's not a transpose up there, that's just an x, plus mu I transpose sigma to the minus 1 mu I, and that one's with a minus sign, and then plus ci. So that's for that part of this rule. Now this term is only dependent on the class and not on x. So I'm going to call that one minus theta I, so that we can just pack the whole thing into a constant. This term, we'll see, will come up on both sides when we expand our rule. So let's move this up here, and so now the rule becomes, if we've got our rule from here, this is the rule that we're taking at this point. Just go out very slightly so I can fit both in as I do this. So the rule now becomes minus x transpose sigma to the minus 1 x plus 2 mu I transpose sigma to the minus 1 x minus theta I is equal to the maximum value over j equals 1 to m of minus x transpose sigma to the minus 1 x plus 2 mu j transpose sigma to the minus 1 x minus theta j. So here I've just substituted this into this rule to give us this line. Okay? This is also done on the slides, but I wanted to go through point by point because it's a really sort of key point to what we're doing here. Can we cancel anything on this line? What can we cancel? Yeah, so this term here and here we can cancel because they're the same on both sides. So we can subtract those out. So actually what that means is that 2 mu I transpose sigma to the minus 1 x minus theta I is equal to the maximum from j equals 1 to m of 2 mu j transpose sigma to the minus 1 x minus theta j. So now, if I now write this mu I transpose sigma to the minus 1, this is a bit awkward, so what I'm going to do is substitute this out. I'm going to write Wi, or Wi transpose, is 2 mu I transpose sigma to the minus 1. So mu I transpose sigma to the minus 1 gives us a row vector, and I'm just going to substitute into that. So this is just a simplification I'm going to make here. This is just, I'm going to set this vector equal to that value. And what I then get is Wi transpose x minus theta I is equal to the maximum value from j equals 1 to m, W transpose x minus theta j. So this will be Wj on this side. So this is now quite nice. So what's happening on each side here? Can anyone suggest what action is taking place in terms of what calculation do we make? So we've got an x, we've got Wi's, theta I, and we've got Wj, theta j on that side. What's actually happening? Could somebody describe what I have to calculate? It's a linear operation, yeah? So this is a, what's this? It's a dot product, it's an inner product that we're calculating here. And then this is just an adjustment to that value, an addition or subtraction. Theta is used to mean a threshold. So actually what this means is that we take an inner product with x, maybe subtract a threshold, and choose the maximum value. So what this corresponds to is actually the idea of a linear discriminator, linear action. So we've got our W that might be here, and we look at multiplying our x as a dot product with that. So this might be our x. We take a dot product between W and x to give us our value. And so this is a linear classifier. So it's actually a piecewise linear classifier. And so what the boundaries that you end up with, the decision surfaces, take our space and divide it up into things that are divided by straight lines. Yes? So we subtract the threshold from both sides just because of the way that the calculation has come up. In fact, there is a further simplification from this that we can do, that if we've got just two classes, then we end up with a single vector that we use instead. I'll come on to this in a moment, and then hopefully that will make a bit more sense. That's right. So if we're in 3 dimensions, then you create a sort of hyperplane, and that's the surface that you get that comes out from this. So this is the thing that we get if the rules mean that these two covariance matrices are the same. So this is an example. If you've already looked at the assignment, in the assignment we assume that the covariance matrices of both classes are the same. And if that's true, then you'll get these linear decision surfaces come up.
Just explain that last step of how you get to a piecewise construct. So, struggling to see how you would end up drawing that piecewise picture.
Yeah, so I'm jumping forward a little bit here, but that's just to give you an idea that there is this whole equation is only dependent linearly on x. and so therefore all the things in here are going to be straight lines rather than anything else. So going back to the projector, going back to the slides that we have. This is really where we end up with this last part of this slide here. So we're using this identity here. We're just unpacking that identity, and that's what we get as this piecewise linear classifier with this x transpose sigma to the minus 1 being a matrix in here. But what we're going to do in just in the next step, if we make a couple of other assumptions as well, if we assume that not only are the classes the same as each other, but they're also equal to the identity, then that rule only becomes dependent on the distance between the mu I and x. And this is where the idea of a nearest mean rule comes up if we also assume that the prior probabilities are equal. So if these are equal, then this probability ends up disappearing from here, because P of omega j and P of omega I are the same, and so therefore our rule ends up as the nearest mean rule. So this is a particularly easy rule for us. It just says that we have our classes. If we've got two classes with means here and here, the identity covariance matrix means that they're sort of circular as we describe those, and the nearest mean rule means that essentially we divide a straight line halfway between those two, and if we're in this side, then we assign it to that class. If we're on this side, we assign it to that class. Now this is something that we could have decided. Yeah, question? If it's on the straight line, that's an interesting question. We're at the point where the probability of assigning to both classes is equal. So what should we do in that case? Does it matter which class we assign it to? Could we assign it to either, or what should we do? Yes, we do. So we have to assign, if we're exactly on the line, we have to assign it to something, but actually no matter which class we assign it to, the error that we end up with is the same. So it's either the error is caused by that class if we assign it to this one, or it's caused by this class if we assign it to that one. But that's, in a sense, it's a free choice if all you're measuring is the error. So does that mean that which error? The Bayesian error, yes. Yes, so on that line, you can randomly choose to assign to either one class or the other, and essentially your error will be, if the classes were equally likely, your error would be 50%. So, but you do have to take that into account when you write your code, because you have to consider the case where the two classes might be exactly equal. Otherwise, if you say, if it's greater, assign to one class, if it's less, assign to the other class, you might end up not making a decision at all about the other one. And if you don't assign it to either, then that could be bad. You might have a preference, but it's up to you which one you use. So the nearest mean rule ends up giving us this particularly easy classification for two classes. If we have more than two classes, then we end up with a piecewise linear boundary. So this boundary is here. We've got a two-class case. If it's more than two classes, the nearest mean rule between, say, three classes here, here, and here, we'd have to have there'd be a nearest mean line here. We think between these two, there's a nearest mean line here. Between this one and this one, there's a nearest mean line about here. That's a bit too far over. Let's say about there. Nearest mean there. So that's the nearest mean that applies in this area. This is the nearest mean that applies in this area. This is the nearest mean that applies here. And we sort of have to work out which one's going to apply down here. So that's the, we'd have to work out what we do in that area in the middle by working out, okay, for this point, is it closer to this one, or this one? Well, in this case, that one to there looks like it's the nearest to there. We'd have to sort of do the calculation to work out what we do in those points. But it will give us a piecewise linear section from here. In fact, I think my drawing is not a very good drawing. They shouldn't overlap in that way round. We ought to actually end up with something. They should all meet at a point. Yeah, that's right. So that's the point where it's equally distant from each of those, and that's the point that it meets at. So actually we can see those illustrated on the next slide for this one. So here the nearest mean rule applies if the covariance matrix is equal to the identity. Here we've got an example where the covariance matrix isn't equal to the identity, but because the covariance matrices are all equal, we still have a linear rule. It's not quite the same as the nearest mean. There's an extra weighting that goes on, but it's still linear. If the covariance matrices are not the same, and we can see here one of them's distributed this way, one's distributed the other way, then we'll end up with a quadratic boundary in general. So it might be a parabola, as somebody said like last week. It might be an oval, depending on the relative weighting of those. So an oval would carve out a particular space in the middle where you'd assign it to one class, and the rest of the space would be assigned to the other class. That's an interesting question. I don't know, actually, off the top of my head. I'll come back to you on that one. Yes, you had a question. Mm-hmm. You can, by integrating over those, in theory, you could, yes, work out the probability that each one will be assigned to each class. So you could do that calculation. And in fact, in the assignment, you'll be working in I'll talk about it after the break, but what's nominally a two-dimensional problem, but really boils down to a one-dimensional problem. You can do the integration to say, what's the probability that the correct one will be assigned into here, and then what's the probability that actually it will be assigned to the wrong class. So it's not straightforward in this, because you need to do an integration over the tails of two-dimensional Gaussians, which is a little bit tricky, and in practice you might end up doing that numerically. But in one-dimensional case, you can actually, or in simple two-class cases, you can do it theoretically by using the so-called error function, the function of the tail of a Gaussian, and we'll talk about that after the break. Okay, so just to then move on to the two-class classifier, we did some of this work in the two-class case, but in general, so I've done this sort of on the slide already. But if we've got equal covariances for the two-class case, we can actually subtract the two sides from each other. So let me have a look at going back to that, just to actually, it's all on here. So when we look at finding the maximum condition, either mu1 is going to be maximum or mu2 is going to be maximum. So we just need to subtract one from the other to find out which is the largest. And so that is this, we've got a vector w here, multiplied by the difference of the two means, added to a constant that is our threshold value that we had before. And so this, we can pack this into this vector W. So this is X transpose W or W transpose X, whichever way around you want to put it. That's the inner product. And then you've got some constant that just tells you how far along your boundary. And this is a very classical pattern recognition system, multiplying by this weight vector and comparing by constant. And essentially you say, if this is bigger than 0, then assign it to class A. If it's less than 0, you assign it to class B. And this is known as the perceptron classifier from about 1950s. So it wasn't originally derived from the Gaussian classifier, but this just shows that, you know, if you make certain assumptions, this is what will come out. And the interesting thing about this this classifier machine is that often it's a really good model. That for simple problems, if you've not got lots of data, this can actually solve many problems that you've got. If it's simple enough that things are nicely separated, you can just use this model with a weight vector. But the thing about the perceptron model is that there is actually a learning algorithm that allows you to update your model. We're not going to go into it in this lecture, but it allows the weight vector to be updated based on whether or not you make mistakes. And in outline, you start off with a small random value for W, for our weight vector. You test it on one of your points where you know the answer. If the machine makes the right answer, you leave it as it is. But if it makes the wrong answer, if the output is too small, you add a bit to W. And if the output is too big, you subtract a bit from W. And then you carry on, and eventually it will find the right answer. And the perceptron learning algorithm is it's provably able to stop as long as the things can be classified. So, and this is one of the work from the 1950s where you could actually do this. And this gave the first sort of interest in these AI machine learning type algorithms was really quite a long time ago in terms of what these algorithms could do. And this is the picture of really how it works. Yes, question?
For the perceptron, how do you know what amount of perceptron? How do you know which one you need to add perceptron? Or is it not? Or is it not?
Yes, so there's the threshold. The constant threshold on the end here is also something that you need to adjust, but you can treat that as let me just do this on another piece of paper. So if we've got the perceptron, let's just go out. If we've got the perceptron where it's W transpose X plus theta is greater than naught, is the question that we want to ask. Actually, we can think of this W as a W1, W2, W3 up to Wn. Our X is X1, X2, X3 down to Xn. But if we augment that by having a W1, which is added an extra term, W0, W1, W2 down to Wn, and X is 1, X1, X2, X3 down to Xn. If we calculate W1 transpose X, that's equal to W0 times 1 plus W1 x1 plus W2 x2 up to Wn xn, which is W0 plus our original W transpose x. So actually, we just need to make that W0 equal to the threshold. So the way that we do it is we just add an extra 1 to expand our input. So our original inputs are there. We just add an extra constant 1, and then we treat that as part of our learning machine. And that means that this W0 becomes the same as the threshold. So we don't really cover the perceptron in detail in this lecture, but if you look at that, that then means that this threshold theta, that's just the same as that W0. So that means that the theta is also learnable. So the threshold is also learnable in this model. So if you're interested, you can look at papers by Rosenblatt, 1952. You might have to go to the library, ask them to bring up papers from the stacks, but actually probably somebody has scanned this one in for you, so you can probably find it on the web sometime. So this is really one of the really early learning algorithms for things. It's I'll scan this in so it's available, but let's go back to the point here. So the linear discriminator here, as long as we know that these two are a two-class problem and they're equal covariance, then we can use this linear discriminator. And this is the simplest type of neural network that you could build. It's a single unit, so it's not a network. And it's certainly not a deep neural network. It's a single layer neural network. But your inputs come in here. One of them will be a threshold value. So here, this one, they've tacked it on the end of this one. X of d plus 1 is equal to 1. And this is the learnable threshold. And you have a threshold at the output, and that classes it into class 1 or class 2. Or class 0 and class 1, depending on how you do that. And this has been used as a basis of neural networks for a very long time. So sometimes this threshold is different. So in the type of neural networks that I was working on during my PhD in the late 1980s, everybody was using smoothed versions of this, a sort of sigmoid function. More recent deep learning networks use a sort of hinge function, a rectified, so that the negative bits are cut off, but you have a sort of linear ramp on the positive side. So there are lots of different functions that you can use for that. But for this simple version, we're just making a yes-no decision about which class to put it in. Okay, so I know I've taken quite a bit of time to go through just a small number of slides here, but really this is the core part of these classifiers, and the Gaussian classifier is really so important. In more practical systems, one of the useful types of classifiers is the so-called Gaussian mixture model, where here we've assumed that our classes are made of a single Gaussian, but actually suppose your classes were a bit lumpy. There are some subclasses inside. You can make each class and model that by a weighted mixture of some Gaussians. And that's actually a very successful model. And so even now, as alternatives to deep learning, you might find models that are built on these Gaussian mixture models. Again, we don't really cover them here, but the principles are sort of the same. So I'm going to take a break at this point, but what I'm going to go on to next is what we've really just touched on for the perceptron is that we want to be able to learn the model based on data where we know the answers. And this is the so-called supervised learning approach, and we'll go on to how to do that in the next session. Okay, I'll take a break now and see you at 11:01. See you after the break.